This is lecture 16, example 1. We have a timing example here. Hopefully this will go much smoother than the last one, with any hope. Yep, great diagram. And so this is our little program, and we want to show how that program looks on the timing diagram. And so a couple of things to notice about this program is there's no load instructions. That means all these instructions here are going to be two-cycle instructions. So that's going to give me a quick start on this. I can write these first two instructions down immediately, but I'm not sure whether it takes the branch or not. And so I'm going to do these first two instructions and then to figure out whether it branches, and then I'll continue on from there. And actually, when I get done here, it looks like I got another jump instruction down there I have to deal with also. So there's two issues why I just can't like write these instructions down real fast. And so what else do we see in this thing? Also the I/O bus in. I don't see any I/O instructions here. This might be an I/O, but I don't see any load instructions. So I/Os, I can tell you for sure I/O is not used in this one, and we'll try to figure out other stuff as we go along. So let's crank through this thing. Let's do it. First two instructions. Once again, I copied that program down. I'm looking at it on a separate piece of paper right now, and that's going to be add I x10, x10, and 5, and this is a BEQ x10, x11, dog. Okay, and that's all I can do on that one. I do know really quick, like I'll speed this up, is that it does do a fetch and execute. And the PC, I think I have a PC starting value. It's actually, it doesn't say here's the PC, it says cat. So cat is at 80, and so this right here is going to be cat. So we can fill that in, 0x80. That means the next instruction is going to be at 0x84, and that's all I can do because I don't know whether it takes the branch or not. We'll figure that out in a second. This is the PC write. PC write's asserted in every execute cycle for every instruction, and so I can just go fill that in. I can just fill out in the whole table because I don't have to worry about load instructions. They're all two-cycle instructions. Okay, looking good. Register write. I can do this for the first instruction. This add I instruction writes register x10. That's going to be turned on as part of the execute cycle of the instruction. And I know for sure branch instructions do not write the register, so I don't have to worry about that. I can fill that out. This is the memory write enable, which I'm going to use when I'm writing to memory, data memory. Neither of these instructions write to data memory. Okay, and read enable. Read enables always the same thing, so I can essentially finish this line. Read enable asserts in the fetch cycle of every single instruction. That's one of our givens for all the instructions. Looking good, and this is a memory read, so this is memory read of data, not instructions, so neither of these first two instructions read memory. So essentially, we can actually look at this thing and see if, well, do any of these instructions read memory? No, we got a store instruction up there somewhere, but none of these instructions read memory, data memory, so I can turn that signal off. Okay, looks good. Okay, so ALU function initially, I don't know if any of this stuff is because it's associated with the last instruction. I can just fill those in real fast. And so ALU functions for an add is going to be 0, 0, 0, 0, which I pull off the schematic diagram. There's a little chart over on the left. ALU source A is going to be x10. It's x10. I'm calling this off the program description. I need to choose the register, so it's 0. Okay, so we'll go fix that in a second. Source B is the immediate value, which is the I input, I immediate input. I have to break out my chart here, which connects to the 1 input of the mux, and that's going to be 0, 1. PC source on this one, this is just a normal instruction. Don't have to worry about it. And so that's going to be 0, 0, which chooses the PC plus 4. And the register select here needs to get the result of the ALU into the reg file, which is going to be 1, 1. So we do have these 2 inputs here. We'll put some question marks up here, just because, save some space. Okay, we're not using this, so we can just blank the whole thing out. We don't really care what that is, but we can figure this out. RS1 for this instruction is the data coming out of X10. The data coming out of X10 is given by the problem. You find my problem here, and it is 0x40, 0x40. Oh, wrong one. 0x40. Maybe we can use that. 0x40. The other piece data coming out of RS2 is we don't know what it is, and so I'm going to put question marks there. But that data that's actually not coming out of the register. It's coming out of the immediate generator, which is a 5. You can see it as part of the instruction right there. The 5 is going to be plus 40 plus 5, which is going to give an output of the ALU, or the input. The thing that's being written to the reg file is 45. Okay, so good. We finished those instructions. So yeah, well, whatever. While we're down here, we can do the next instruction, which is this branch, and the branch instruction is going to send X10 and X11 to RS1 and RS2. So X10 got written with a 0x45, which is this value right here. And X11 I need to pull off the problem description, which is also handily 0x45. Oh, big shocker there, you know. Okay, so nothing's being written to the reg file there at that point. So this is a, we don't really care what this is. You know, working our way up on this. ALU function, this is not it for a branch instruction. This is a don't care, it's not used. We're not using the ALU, so this is a don't care. ALU source B, we're not using the ALU. It's a don't care. PC source, it's obviously going to take the branch because these two are equal. So it's PC source, have to choose the branch option, which is 1, 0. Now look, I pulled this off the PC mux inputs. And lastly here, read write select is a big don't care because I'm not writing the register. And so that's what I got so far. Looks like it did take the jump. It jumped to dog. And so we're at dog. I have to figure out what dog is. So it jumped forward by 1, so 8488. This becomes 8C. Oops. 0x8C. The instruction at dog is SB. SB X11 4 X30. Okay, so it's going to do a store instruction. Store blah blah blah. When I'm storing something, I'm not writing it to the register, so I can turn the register write off. The memory read, no, it's memory write. I am writing something. I'm writing something to memory, and so I need to turn that memory write on right there. And I think that's it for the top instruction. So I can come down here and fill in the data. It is a memory access, and so I need to use the ALU to formulate the address, which is 0000. Source A is going to be, it's going to choose the register output. Source B, this is an S-type, it's a store instruction. I happen to know store instructions are S-type instructions, and so it's going to choose the S-type input. For source B, which I don't know, I have to look at it, it's actually a 10, and I'm looking at the schematic diagram. That's where I'm pulling this data from. Okay, so PC source, it's a normal instruction. It just advances by 4. Read-write source here is I'm storing something in memory. So this is a big don't care here. I don't really care what's going into the reg file, or what the select signals are. Okay, reg file here. I don't know what's going in. I'm not using the reg file, so I can just keep that as a don't care. And I should be able to figure out these sources here. So RS1 is the value in X30, and I believe that's given as part of the problem. 0xC0, that's the base register offset. As far as the RS2 goes, it doesn't use RS2. The actual data is coming out of the immediate generator, so the RS2 is a big I don't know on that one. Well, heck, we're done with that. So the next instruction is SLLI X11 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 1. Okay, looking good. So we can go crank through this. The address of this thing is going to be 4 plus 8C, which is 0x90. SLLI, it does in fact write the result to a register. Okay, and memory, is it accessing memory? It's not accessing memory. So we can clear that one, and God, we're almost done with that one. Let's see what we got going down here. ALU function, I need to look at the cheat sheet and select the shift left, which is the 0001 input, and that selects the shift logical left operation, and I'm going to use the register output for the ALU source B, and this is an immediate instruction. I can see it's an immediate, so I need to grab the immediate input on that mux, which happens to be a 01. This is the lower ALU mux. The PC source, nothing remarkable about this. It is not program flow control, so it chooses to advance by 4. This does need to write the result from the ALU back to the register, so this is a 1-1. And let's see what we got here. So the thing that's being written back is, God, what's being written back here? Well, we can do this. The data is coming out RS2. It's an immediate instruction, so I don't know what that data is, and I don't really care about it. But the data coming out of the register is X11, and I don't think I wrote X11. So X11 is still 45, 0x45. And so I'm going to say it's shifted left. 45 is shifted left by 1. So 45 shifted left by 1. You know, multiply that by 2. It looks like it's going to be a 9a, right? 0x9a. And so I almost feel like doing that just to make sure that's right. 9a, 8, no, so 8, it's 8a, how's that? 2 times 4 is 8, so this is an 8a. Here, I better clean it up. 0x8a. So 45 times 45 times 2, you can do the math on this. This is 8a. Okay, looking good there. Next instruction, SLLI, is going to be a JAL. JAL cat. So it's going to take a jump. It's going to jump back to cat. So the instruction at cat is, oh, yeah, I got it doing it wrong. That's okay. This is JAL. JAL cat. The instruction address of cat is given 0x. That's where it jumps to. So 0x94 is the instruction. It jumps to cat, which is 0x80, and then it goes to 0x84 for the next instruction. And so heck, we're done with the PC line. So after JAL, it jumps to cat, and it essentially redoes this instruction. ADDI X10 X10 5 goes on to the next instruction, which obviously we're not going to fit that on there. So it looks good. Here we are at the JAL. If in doubt, I read the spec. JAL actually does write a register, so I need to turn that register right on. This add instruction here is also going to write a register, so I need to turn the reg right on there, and then I'm done with that line. Neither of these instructions here write memory, so I can fill that in, and look, heck, I'm done with that line. Isn't that great? I'm almost done with the whole problem. Okay, so this is the jump and link instruction. It doesn't use the ALU, so I don't really care about that, which means I don't really care what ALU sources are either. PC source, it is a JAL, which means I have to look at my cheat sheet because it takes the JAL option, which is a 1-1 unconditional jump. JAL, is that right? Yep, that's right. Okay, and the RF select here, it is writing the register, and it's writing it with a PC value, so I need to get that right. The PC is coming into 00. Yeah, looking good. Reg file here that is the thing that is coming into 2x or whatever. It's the thing that's coming into the register file, which is x1 by default. It's PC plus 4, so it's 4 greater than the current PC 0x98. So this is the current PC, so a 98 gets written in there, and that's why this data is 98. It's 4 greater than the PC for this JAL instruction. RS1 here. These are jump and link instructions. Heck, I don't use jump and link, so these are just junk data. I don't care about that. Yeah, wow, almost done. Add instruction. We can just fill these in. I know ALU fun has done this enough time, is 0. The source, register source is 0. ALU source B for an immediate instruction. Checking my spec again. Choose the immediate option, which is 0-1. PC source. This is a normal instruction. It advances by 4. It certainly does write the result, ALU result, back to the register file. So I'm going to choose a 1-1 to route that from the ALU result back to the reg file. And then hopefully these aren't too hard either. Okay, so X10 it's given in the problem as 40, but we did add 5 to it, so it's actually, at this point, it's 4A. 0x4A. That's what's being written. What's being sent to it is 0x45, which is the new value, and this is, once again, it's an immediate value, so I don't know what that value is. And you know what? I think I'm done with this problem. Hopefully, did better than the last problem. Once again, there's many ways to do this. I never, I just do them different ways every time. Very instructive problem. If this is really seems hard, no doubt it is hard, but if you can do this, you know that everything there is to know about this processor practically. So I encourage you to step through these problems. Yeah, I cut that off too soon. Step through these problems, go through it one step by step, and you will not regret that.